Okay, problem 10.67 is a tough problem. It's going to have a hanging pulley, and this pulley is no longer our friend, the frictionless one. We have to care about the weight, and we have to care about it spinning, and we're asked an even weirder question. We're asked, what's the force on the hook up here? Okay. Which again is the kind of question that we've really never had to think about before. And again, it sort of makes sense because it won't be just supporting both these things, because both these things are falling like this, or well, one of these things is falling, this one's falling down, and this one's being lifted up. So depending on how much one is falling and one is lifting up, that's actually going to make a difference in what we get in our answers. Okay. This sounds weird, but it's going to make a difference. Think about the free body diagram here. Okay, maybe. Okay, we've got the force of the hook, and it's holding up both ropes. Remember, they won't be the same because both of them are going to provide tension here. So there's going to be T1. I'm going to call this object 1. Okay, and it's going to have T2 for object 2 over here, and it's also going to have mg just from the actual, has to hold up the pulley itself. Okay, so it's got to balance all those things. So F for the hook is going to be T1 plus T2, terrible plus sign, plus M, I'm going to call it capital M, G. Okay, so the hard part of this problem is coming up with T1 and T2. That's where all the rotational things have to come into play. Okay, so let's start by making a basic rotational equation for it. Okay, and the two things that are, the hook is pulling through the center, so we know it don't want to have a torque, and gravity's pulling through the center of the pulley, so it also won't have a torque. The only things that will are the two tensions that are acting on it. Okay, and they're going to oppose each other. You can see that the heavier block is going to be block 2, so it's going to pull down. So we're going to say that the equation is going to be RT2 minus RT1 equals I omega. Okay. I chose T2 to be the one that is going to be larger because I know T2 is going to be bigger than T1. I know it's going to cycle in that direction. So I chose the bigger force minus the smaller force, or bigger torque, sorry, minus the smaller force. Both the radii are going to be the same. And actually factor that out to RT2 minus T1 equals I alpha over, I'm going to divide both sides by R in a second. So T2 minus T1 equals I alpha over R. Okay, and we know that's going to be a solid disk, so it's going to be T2 minus T1 is going to equal I alpha over R. Okay, and I is going to be 1/2 M, I use capital M for the disk, R squared alpha, all divided by R. That's going to be 1/2 M. One of these is going to divide away, one of those is going to divide away. And here's our usual trick. R alpha is going to be the acceleration. So T2 minus T1 is going to be I, not I, sorry, 1/2 M A. So we've dealt with our torque equations. Our next job is going to deal with the actual force equations, the forces acting on each of the blocks. So now we need to consider the forces. Let's start with object 1 over here. Okay, so that's object 1. Remember, we labeled it that way before. So if we add up the forces on it, it's going to be tension 1. Remember that now that we have a pulley, we can't call both of those the same force, the tension on both sides, okay, because it's each putting a torque on the wheel. So minus M1G equals and this is going to accelerate in the upward direction. So we're going to call it M1A, and we're going to leave it as positive. Okay, so that's going to be, I'm going to put numbers in too. We know this is T1 minus 75 newtons equals 7.65 kilograms all times A. I got that 7.65 by dividing the 75 newtons by 9.8 meters per second squared. So I got one equation for that, which means that T1, I'm going to actually make an equation for T1. It's going to be 7.65 A plus 75. I'm actually taking the units out of it because we're going to combine some equations together. Okay. Now let's look at object 2 over here. Okay. Its equation is going to be T2 minus M2G, remember they're the same two forces, equals, but we know this is the heavier block, it's going to go downwards, so we're going to have to call it negative M2A. Okay. And we're going to put all the numbers in there. So T2 minus 125 newtons, remember that's a given in the problem, equals negative 12.8 kilograms. Again, 125 divided by 9.8 A. Okay. And then I'm going to put all of those, move all the T2s to the other side, or all the things that are not T2 to the other side. So T2 is going to equal, and I'm going to take the units out too, 125 minus 12.8 A. So now I've got two equations for T1 and T2, and now I can substitute all that stuff back into our Newton's second law for rotation equation that we made before and put all that stuff together. Remember that equation is T2 minus T1 equals 1/2. I'm going to put in 5.1 kilograms A. Remember the 5.1 comes from that 50 newtons. I divided that by 9.8. So I'm going to pop that back in. And I'm going to put all these things in one big long equation, but I'm going to move that to another page for us to do it because it's way too busy to put here. Okay, so again, the equation is going to be T2 minus T1 equals 1/2 5.1 A, which I'm going to go ahead and call 2.55 A. T2 minus T1. Then we're going to substitute those two equations together the way that we did before. So T2, remember, is going to be 125 newtons minus 12.8 A, and then it's going to be minus 75 newtons plus 7.65 A, all equals 2.55 A. Okay, so now I'm going to move all the A's to the, well, I'm going to distribute this first. I should do that. So 125 newtons. I'm going to move those over to minus 75 newtons minus 12.8 A minus 7.65 A equals 2.55 A. Okay. I'm going to bring all the A's together. Well, let's subtract these first. 50 newtons equals 2.55 A plus 7.65 A plus 12.8 A. Okay. So, okay. And if I do all that together, I get that 50 newtons equals 23 A. I get that A equals 2.17 meters per second squared. We still seem really far from the answer. And the reason we seem that way is because we are pretty far from the answer, but not as far as it looks like we are. I'm going to clear a page and we're going to calculate what the tensions are. Once we calculate the two tensions, it'll be easy to come up with the force on the hook. Now we're solving for the two tensions. So we know that tension 1 is going to equal 7.65 times A, which is 2.17. This is kilograms. This is meters per second squared, plus 75 newtons. Okay. I put all that together. I get a tension of about 91.6 newtons. I'm going to find the tension on the second rope, this one over here. Okay. And that's going to be 12.8. Oh, wait a minute, that's not right. It is right, that's 12.8, but it's in the wrong order. 125 newtons minus 12.8 kilograms times 2.17 meters per second squared. Okay. Do all that, we get 97.7 newtons. Okay, so now we actually have almost all of our forces. Remember we said the force of the hook is going to be the tension of the first rope plus the tension of the second rope plus mg. So that's going to be 91.6 newtons plus 97.7 newtons plus 50 newtons. I didn't make that up out of thin air. It's up here. If I add those together, I get 238.8 newtons. Okay. And if you look, that is less than the amount that you would need to lift it. That amount would be 75 plus 125 plus that 50 again. That'd be 250. It should be less because it's not lifting all of the blocks. It's some of the block is accelerating down, so it doesn't need to lift at all. Okay, so that's the answer, 238.8 newtons.